So the next presentation is going to be on the effects of soil types and vibration and liquefiable soils. And here to present is Bob Hannan. Since joining WJE in 1976, I was in kindergarten at that time. Bob has concentrated his experience in the measurement and analysis of vibrations and the development of data acquisition systems and techniques for measuring dynamic stress conditions in structures. He has conducted condition and documentation surveys, construction vibration surveillance projects, and the investigation of several structural failures and collapses. He has also been instrumental in developing procedures to test material properties of such things as security, glazing products, cardboard, marble, granite, and plastics. Bob has developed several PC, static, and dynamic data acquisition systems for monitoring vibrations, strain, deflection, tilt, temperature, humidity, and pressure in buildings. He has successfully used vibration sensors to measure load in bridge cables and to locate the origin of popping noises in walls and windows. He has also implemented a video webcam with remote vibration monitoring system to identify sources of traffic-related vibrations. So I'll turn it over to Bob. Thanks, Bob.
Thank you. I realize that my presentation might not be quite as elaborate or energetic as Arnie's. He does quite a few more presentations than I do. Can you hear me okay? Okay. My first talk is about the effects of soil type on vibrations. Generally, to give you a little bit of an overview of what I'm going to talk about, or the results of what I'm going to talk about, is that vibrations attenuate at a greater rate in soft soils than hard soil or rock. And then the fact that high-frequency vibrations attenuate at a greater rate than low-frequency vibrations, and that not all soils are susceptible to liquefaction. That's a very generalized statement that you have to take into account, because there's some engineers who are of the opinion that any soil is going to result, vibrations on any type of soil is going to result in settlement due to either consolidation or liquefaction. And liquefaction is a slightly different phenomenon than actual soil consolidation. I expect maybe that there will be some questions. Talking about vibration attenuation, there are two basically different methods that lead to attenuation of vibrations with distance traveling through soil. The first is a geometric or radiation damping that occurs. And it's basically just due to the fact that as vibrations travel from the origin, they are spreading out over a either spherical or circular area, and so the energy dissipates with distance. And there's a formula, a general formula, to be able to calculate the attenuation of vibrations over distance, where you have amplitude 2 is the farther the measurement made at the greater distance, R2, and amplitude 1 is the amplitude that you would measure at a close distance. And this is based on the idea that you would actually know the amplitude at radius 1. And it's the amplitude 2 is equal to the initial amplitude times the ratio of the closest radius divided by the farthest radius raised to the power of n, where n is the attenuation coefficient that you would apply to that particular type of vibration wave, where there's a Raleigh wave. It's one of the body waves that travel through the ground. And then normal body waves. There's a whole variety of different waves that travel through the ground that are produced by typically an impact. And then for surface waves, they're essentially saying that the attenuation of surface waves occurs at a much more rapid rate. The vibrations on the surface dissipate quicker than any body waves in the ground. Another type of vibration attenuation is material or hysteretic damping. Where with material or hysteretic damping, they've added a factor that deals with the damping properties of the soil, where you get into a little bit of the material aspects. And that's the exponent E. It's a logarithmic component, and it incorporates an alpha, which is the damping, essentially an attenuation damping coefficient. And generally the alpha value or the damping coefficient is greater in soft soils. And because you're raising E to the negative alpha power, having a greater alpha value actually causes the vibration amplitudes to decrease at a greater rate for a given distance. Alpha also is frequency dependent. So high frequency vibrations tend to have a higher alpha value than low frequency vibrations, which implies that high frequency vibrations attenuate differently, or high frequency vibrations attenuate at a greater rate. And you can actually, there's a formula for calculating, if you know the alpha value for a particular frequency, you can calculate the alpha value for any other frequency, and it's a fairly simple relationship, such that at a higher frequency, the alpha value goes up. And the alpha value is the rate of attenuation, so at a higher rate of attenuation, or you get a higher rate of attenuation for a higher frequency vibration. And there are documents that provide estimates of the alpha value for different types of soil. And here's where you get a little bit of ability to identify the characteristics of different types of soils. There are classifications for soils that were developed in the 80s for like a weak or soft soil, where they have some general methods for being able to identify which class of soil. In this case, a weak or soft soil is one that a shovel can easily penetrate. It's identified as class 1, and it has a very high attenuation coefficient, alpha. And these are values that are estimated at a frequency of 5 hertz. So if you know the vibration frequency that is going to be produced at the site, and it's different from 5 hertz, you can calculate what that alpha value, how that alpha range can shift. And this covers a range of values for each class. So class 2 is a competent soil, and that might be what you might experience mostly in areas where the soil has already been there for a long time. It's a fairly relatively stable soil, but it's still a soil, and it can be dug easily. That's called a class 2 soil, and that would be most sands, sandy clays, gravel, silts, and weathered rock. And then class 3 is a hard soil. You cannot dig with the shovel. It would be dense compacted sand, dry consolidated clay, consolidated glacial till, and some exposed rock. It's very hard. The alpha value is very low, which indicates that vibrations would not attenuate very fast with increasing distance. And then hard competent rock has a much lower attenuation coefficient. They also have in there the N values that you'd obtain from soil borings, and to make it even more complicated to try to estimate how vibrations might transmit from a source, you have to take into account that you get different blow counts or different N values for soil at different depths, below the surface. So vibrations may travel better in lower strata that may have higher N values and therefore lower attenuation rates, where the surface soils may be much softer and would transmit the low frequency vibrations better. This is just an indication from that document that actually talked about the attenuation coefficients, showing basically that the class 3 soil, the harder rock, or harder soil, more competent soil, has a lower attenuation rate than a class 2 soil. It's just kind of an illustration comparing the attenuation rates between two different types of soils. There is another document that I've come across where it actually gives a method for estimating vibration amplitudes that could be produced by pile driving activity. And this in particular would be impact pile driving, not necessarily steady state vibratory pile driving. It basically, I guess for like the type 3 soil, has a lower attenuation rate. So for a given distance, the amplitude is higher. And for different energy levels, starting at 10 kip-foot of energy, you can estimate the vibration level for a type 2 soil at any given distance. It takes into account the energy of the hammer. So at a higher energy hammer, up to 640 kip-feet, you'd get significantly at a given distance of 100 feet. For the low energy hammer, you'd be about 0.08 inches per second. But for the 640 kip-foot hammer, you could get up to about 1.2 inches per second. Well, no, like 0.9 inches per second. But that gives you an idea of the fact that there are significant differences in the soil type and how that comes into play, and something that you would have to take into account when you're trying to estimate the effect of vibrations on the surrounding buildings. So generally, in terms of the effects of soil type on vibrations, to reiterate, the vibrations attenuate more in soft soils than in hard soils, and that high frequency vibrations attenuate more quickly than low frequency waves. And the explanation for that part of it is that amplitude decreases in magnitude with each oscillation as the wave travels from the source. Low frequency waves are oscillating at generally about 10 cycles per second, but when you're talking about the higher frequency waves, you get about maybe up to 30 cycles per second of earthborne vibrations traveling from an impact source, maybe up to 50 cycles per second. And in a rock, it may be up to 60 to 100 cycles per second. Each oscillation is going to lose some amplitude as the wave travels along. And the fact that over a given distance, the high frequency wave goes through more cycles. So even though in soft material, the damping that occurs per cycle may be greater than what would happen in hard soil, you're going through many more cycles to cover the same distance. So the high frequency vibrations tend to dissipate out very quickly with distance. And if you have in that vibration time history, the low frequency vibrations tend to win out. They can travel farther, they can go the distance better than high frequency vibrations. There's also the fact that as this dissipation occurs in the soil, some of that energy may get transmitted or transferred to low frequency energy, and may help to magnify the effect of the low frequency wave as it's traveling through the ground. Okay, well then we can talk a little bit about liquefiable or liquefaction and the phenomenon of liquefaction. I haven't done a major research project in it, but I've gotten involved in several issues. And also, one of the key authors in studying liquefaction happened to be my graduate advisor at UIC, Marshall Silver, and his explanation of liquefaction always kind of stuck with me. So I have a kind of a general understanding of the background behind it. Basically, the weight of the soil and the surcharge above it push the grains against each other and cause them to interlock due to friction between the grains. As the soil at the surface doesn't have very much confinement, so there's not a whole lot of force pushing the grains together. So that soil can be a little bit more easily deformed. It has a lower bearing capacity than soil that is buried at a depth. And it's kind of, some of the basics of geotechnical engineering is the concept that the deeper the soil is, the more confinement it has, the greater is its bearing capacity. If you uncover the soil from the point in the ground, you lose the surcharge, you lose the bearing, you lose the confinement of the soil, and therefore its bearing capacity goes down. And it's based on the confinement and intergranular forces that are holding the material together. The confining pressure and the resulting intergranular friction serve to develop the bearing capacity of the soil. In a dry soil, there's an effective stress, which is these intergranular forces acting. You can calculate the magnitude of that effective stress in the soil to relate it to the bearing capacity, but it's based on the dry unit weight of the soil. When you add water to the soil, those grains essentially become buoyant. There's a buoyancy effect of the water that is saturating the soil, and that buoyancy reduces the magnitude of the intergranular forces, and therefore there's less friction holding those grains together, keeping them from sliding against each other. So there, as I mentioned, the intergranular forces are lower in the saturated soil. As a vibration wave travels through the ground, it's considered to be a pressure wave because it's energy transmitting through the ground, transmitting forces through the grains that transfer those forces from one grain to another as the wave passes through. If that vibration wave is traveling through the water, it applies a pore water pressure on the water that is surrounding the soil. It's an isometric pressure acting in all directions. I guess I'm getting ahead of myself here. If the forces, still talking about dry soil, if the forces exceed the intergranular friction, they can displace the grains. And when the grains get displaced, they want to come back together in a slightly tighter orientation. Closer packing is how it's referred to. That process of closer packing is a tendency of the soil to occur, and it's a process that takes place during any kind of consolidation process. When you do dynamic compaction, you're producing this effect where you're displacing the soil grains and then they come back together in a tighter packing. And sometimes in consolidating soil or doing compaction work on soil, you may add some moisture because it helps lubricate the soil, it helps it to come together. You wouldn't necessarily do it on a saturated soil for various reasons that may become evident. If the soil is saturated, the trend toward closer packing results in a transfer of the gravity load from the mineral skeleton to the pore water. That tends to increase the pore pressure. That pore pressure can dissipate with time But in the process of developing that pore pressure, at the instant when the pore pressure goes up, you tend to be pushing the grains apart. They're already confined, pushing against each other, and you develop a pressure that's pushing them apart. You can develop a large enough pressure that actually disperses the grains so they're not touching each other anymore. And that can happen. If the pressure doesn't have time to dissipate between impulses, the pore water pressure accumulates. Each impact or each cycle of vibration will produce a pressure pulse that tries to push the grains apart because it's applying this pore water pressure between the grains. It pushes the grains apart, and each successive cycle tends to add to that if they occur too frequently. There is some time that is required for that pressure wave, that pore pressure to dissipate. Sometimes it can be a matter of minutes that it takes for that pore pressure to dissipate. You're introducing a pulse into the ground, into the pore water, and you get a sudden rise in pore pressure even with the first cycle of energy. And if you don't give it time to dissipate, then the next pulse comes along, drives it up even farther, and it doesn't have time to dissipate out, and you end up building up a pore water pressure. And that increasing pore water pressure reduces the effective stress in the soil because the effective stress is the dry unit weight effect of the total stress minus the buoyancy factor of the saturation of water. And as you're increasing the pore water pressure by adding energy into the system, you're driving up that pore water pressure, you're decreasing the inner granular forces, and because of that, because now you have less friction between the grains that are keeping the grains from sliding, you end up decreasing your bearing capacity. And if you have a structure sitting on that soil, you could end up with settlement because the forces that are being applied to the soil, the pressure on the soil may end up exceeding the bearing capacity if you've driven that pore water pressure up too high. Here's an example from an NRC, National Research Council, paper on liquefaction in soils. This is where a lot of the information that I have on this comes from. It's from the 80s, but it's a study on the earthquake sensitivity or liquefaction of soil, primarily due to earthquakes, but it still applies to such activities as vibratory pile driving or even impact pile driving. There are some case histories that I've been involved in that I don't really have very many of them in here. But the example here is two different soil types. The one on the left is a loose sand, and the soil on the right is a consolidated or dense sand. In both cases, they're saturated, because that's one of the factors that needs to be involved is a saturated soil. In the loose sand condition, it only took about 10 cycles of vibration before the pore water pressure, actually even within the first cycle of applied dynamic pressure, the pore water pressure began accumulating, and deformation began after probably about 10 cycles. I haven't really counted them. It's probably more like 8. In a dense sand on the right, the pore water pressure began building up right away, and it took apparently slightly more.
Sorry. So that's deformation.
Right.
On this count. I don't know if you can see that back there.
Right. It's hard to see. The top graph is the applied load or applied pressure, and they identify the dynamic pressure as 0.7 kilograms per square centimeter. That I didn't try to convert it to PSF. But it's basically, they introduced a square wave of energy into this, and they were measuring deformation at the, it's on actually a confined sample of material rather than an actual soil sample out in the field. But it's basically demonstrating that you get the dynamic, you can measure in terms of pore water pressure. They're measuring the actual pore water pressure, but they see that even though there's a cyclic pulse going on, that the average pore water pressure increases over time. And eventually that average pore water pressure builds to the point where you've pushed the grains apart enough that they start to lose their capacity because they have no, you've decreased the effective stress in the soil so much. Essentially, the way it was initially explained to me in my class was that it suspends the grain and turns it into a liquid like quicksand. And it's the same sort of effect that you have with actual quicksand, where there's, you know, an underground spring where the water wells up and is flowing up through the soil, and you get the upward flow of water disperses the sand grains and produces essentially a liquid. And that's what happens with this liquefiable soil. It's similar to taking freshly placed concrete, putting a vibrator in it, and consolidating it. You'd see it turn into a liquid. It starts out as a lump when you put it down, but you put a vibrator in it, put it to a steady state vibration. That's essentially what's happening, that you're suspending the particles in the liquid by increasing their pore water pressure. Then again, not all soils are sensitive to liquefaction. There are some sensitive soils. It was referred to as recent geologic deposits that are saturated, such as river sands that have not experienced any consolidation activity. Saturated sandy soils without cohesive fines. It's something that we'll get into a little bit. Uniformly grained sands, not grains, that there is in this NRC paper, there's a kind of a description for the grain size distribution. The boundary, the boundaries for potentially liquefiable soils have a fairly wide range of grain distributions, but then there's a boundary. The inner lines define the boundaries for the most liquefiable soils. There's a whole variety of there's a variety of soils that could be liquefiable, but it doesn't cover all soils, or it doesn't include all soils. There's a commentary in the research that when you add clay to the mix, it tends to prevent the pore pressure buildup. And then to get into, because I've already covered the sensitive soils, but non-sensitive soils would basically include dry soils, which would be loose sands. They are not necessarily liquefiable if there's no water present. Even partially just a wet sand is not as sensitive as a saturated sand. Possibly what could happen with vibrations on a wet sand that's not totally saturated is that the vibrations may tend to drive the water off the grains, cause them to settle to a lower point, in which case the saturated water level may raise, and that soil might become sensitive. Now, dry soil could be consolidated by introducing dynamic vibrations, like dynamic compaction, but it's not necessarily sensitive to liquefaction. Clay and silt is generally considered not liquefiable. That's because pore water pressures can't really build up in a clay. Well-graded soils, which gets back to the idea of adding clay to the mix. And essentially, it's identified that uniform grain distribution is needed to lead to liquefaction. Dense sands are not as susceptible because they are already pretty well consolidated. They don't have as much water available in them if they're saturated. An example that I have, which I think Arnie might be including later in his talk about damage to a building, would be a project I got involved in back in, I think, 1998. The Pore condominium. It's a 12-story building in Chicago with a mat foundation, we'd never determined whether it was just a mat foundation or if it was a mat foundation with timber piles below it. It's in downtown Chicago, near North Side, in a particularly vibration-sensitive part of the city, where it's the top 40 feet of the soil is essentially a muck. It's a mix of sand, silty sand, and very soft clays, all of it saturated because it's near the Lake Michigan shore. Water level is not very far below the surface. In this case, we knew the sand that supported the structure was essentially soupy. They tried to do an exploratory pit next to the building and found that as they tried to dig below the foundation, the material just flowed into the hole. So it was not a very good situation. They demolished the building next door, and they took care when they demolished the building to fill the site right away, so they didn't relieve the overburden pressure on the foundation. They came back in a few months later and started drilling caissons, and they did fine. They did caissons right up next to the building without any effect. They had a vibration monitor in the building. At the time, I was brought onto the project to represent the building's interest rather than the developer. And I tried to make sure that they had their monitors operating, and they assured me, yes, we have them operating, everything's fine. I think maybe they didn't, but they say they did. They had an incident out in the middle of the site where a temporary casing for the caisson got stuck in the ground, and they decided to try to remove that casing by pulling on it with one crane and impacting it with a Kelly bar with another crane that they brought on site, or they vice versa. They used a second crane to try to continually pull up on it while they were pounding on it. And they kept that up all afternoon into the evening, and eventually I think they gave up trying to pull it out and abandoned it. The next day they discovered that there was movement that had occurred in the building. The surveyor went to do his normal circuit of elevation surveys and found that he couldn't get into a bike room that was right up adjacent to the wall that was next to the construction work. And they did the pounding on a Thursday. Friday is when they discovered that they couldn't get into this room. By Monday, the stairwell that went up adjacent to that wall was starting to exhibit some relatively significant spalling of the plaster finishes, that it looked like the stairwell was getting twisted apart. So I was brought out to the site to look at it, and the contractor admitted that, yeah, we should have left that temporary casing in place. In the meantime, by the time the settlement eventually settled out, they had about 1.5 inches of settlement of that end of the building, and they discovered that the building was actually 2 buildings that were tied together, and it was no longer tied together. It opened up like a zipper going up the wall. So that was an effect. It was an effect of this repeated impacting, which kind of goes back to the comment I made before. That's not necessarily vibratory pile driving that could affect this. It's repeated impacts from impact pile driving could have the same effect, because it takes several seconds for that pore water pressure to dissipate from the soil, and impact pile driving usually is 1 1 impact per second or slightly faster than that. So with each impact, you can get an incremental increase in the pore water pressure. Let's go back to that one. Because there's another case study that actually came to mind since then, since I finished this up, where there was a building, another one in Chicago, in the near north side, where a contractor demolished or was demolishing a building, or had already demolished a building at this point. They were doing their work right next to a very high-end restaurant, and they were going to end up doing pile driving within about a foot from the foundation wall of this building. And they called us in to discuss the demolition process, and I pointed out that they may be subject to an issue with their pile driving effect. And we had a meeting with the pile driving contractor who admitted that, oh yeah, we always get settlement of buildings when we pile drive next to them. And we just go in and patch the cracks. And the restaurant owners said, no, you're not going to do that, because if we have to close down the restaurant to patch cracks, you're going to pay for our lost revenue for the entire time. We can't have this construction work going on while we're open. And they said that the lawsuits would end up ruining the general contractor. So they just said, let's see what we could do. We did a test on site where I used this concept of the pore pressure buildup. We went out to the middle of the site, put surcharge on the soil, huge concrete blocks to simulate the surcharge of the footing, and they drove a pile next to this block, and we measured the pore water pressure adjacent to the pile, as well as vibration amplitudes. And I had them do the first pile where they hit the pile 10 times. They'd wait 5 minutes and watch the pore water pressure as it built up, and then as it dissipated. Wait till the pore water pressure went down, hit it another 10 times. And they got the pile driven without any movement of the block. Then I said, okay, go ahead on the next pile, drive it all the way down like you normally would, and the pore water pressure built up, never dissipated, kept building, and they got about a 1/4 inch settlement of the block. And so they decided, okay, we'll take the longer method, get the piles installed, and they got all the piles installed adjacent to the building without any adverse effects on the building. When they got to the other side of the site, they were away from this very high rent restaurant. They were next to a pancake house. And they went ahead and pile drive their normal process, and they caused settlement of that building, but they said that doesn't matter. So that's it from my end of it. I think the next one is going to be Nate talking about some other stuff. Any questions?
Yeah,
is there any times that you might want to, if you have the liquefiable soils, to, find the right amplitude and the right frequency to make sure that it does liquefy as a benefit to what you're doing?
To make sure that it does, or just to verify?
No,
sensitivity?
that you try to get the liquefaction as a benefit, like you're trying to get, you don't have any damage to cause anywhere, but you're trying to get the caissons in the ground.
Oh, yeah.
And then you find the right way to do it to liquefy it so the caissons go in easy.
Well, with caissons, usually with caissons, you're augering down to get through. And I think that's a little bit different than trying to drive piles, vibratory pile driving. That's essentially what it's doing. It's dispersing the soil so the pile slips into the ground, and you can tune the frequency, the driving frequency, to a resonant frequency of the soil to get it in. You do run the risk of generating a resonant response that travels farther through the soil in the process. But if you're not too worried about damaging nearby structures, that should be okay. But yeah, you would find that, and if it is saturated, I mean, you could even take the soil and saturate it if you want then, and use that to help you drive piles into it. But then you're also going to generate possibly some soil subsidence. There's a zone of effect. Typically, they say that that range of influence is equal to the length of the pile that you're installing, that there's a radius of influence. But out at that perimeter, that outer radius, you're essentially starting at zero settlement to the maximum settlement directly adjacent to the pile. Anything else?
Other questions? So, thanks, Bob. And